last time we looked at investing $12,000 at an annual rate of 3%.
Whoa, no, we
Is this
did
the
not.
right unit? I just didn't write it down.
No, we didn't.
No,
Yeah.
What?
yes we did.
Is this the right unit?
What are you showing me?
You know, we
My
did
notes.
because you're.
Well, okay, no, we didn't. We never did this.
What unit? What are you showing me?
Is
On
this
the
the
board,
5.1?
Yes.
Okay, that's all I needed to know. I just forgot to write it at the top.
Max.
Could you explain what E is again? Like how?
Whoa, that's the
How
second
can you
noise
find
I've
it?
heard in a while.
How do I find E?
Yeah, like
I
what?
just use E.
Wait, let's just
Like pi is the ratio between the diameter and the circumference. What's E?
E is the limit when you take the financial equation and you take it to the extreme.
I don't remember doing this.
You don't remember?
I have a question.
Well, we should do that.
Is this 5.1 here? Oh my god.
I don't know.
Because
I think so. Yeah.
Okay.
Yeah.
Okay.
Yeah. It's all about
Yeah,
exponents.
isn't it like
Yeah.
the investment thing where you have
The
your
investment thingy.
principal and then you're like 1 plus your
'Cause I don't know where the
percent
rest of
over
my
the
notes
Yes.
times. Yeah,
Right.
We did that.
I have more notes.
Yeah, we did that, but I want to show you again.
Pretty sure we did that, yeah.
No,
So-
we never did any problems on it. He just
We
showed
didn't do
us
any
what it
problems on it. Okay, so I'm
is.
going to
He
show
just
you.
showed us what it is.
I'm going to show you the basis of where that comes from again.
Oh,
Like, he
I'm
showed
so
us what
dumb.
it
I put
was.
my notes where I put the homework that I did.
Okay, so if I have some f of x, if I have a function f of x, and it equals, what's the formula that we have so far?
P times 1 plus your percent over.
Okay, I'm not gonna. So I'm gonna talk about this in a general sense. I'm not even gonna use the principal. I'm not gonna use the rate. I'm just gonna use the bare bones, like just to look at like the behavior of this function. So it's 1 plus 1 over x, and all of this is raised to the x power.
Wait, what are we doing?
And then here I'm going to make a table, and I'm going to say, I'm going to look at, I need a variable called c. I'm going to start c off at 0. And then for my table, I'm going to say c plus 0. And then this will be f of c. So you see that added that dot. There's the point. And then I'm going to say, for my table, I'm going to say c plus 1. Oh, that should be f of x1. And then c plus 2. And then c plus 3. And then c plus 4, and that's enough. C plus 4. And you can see that as I graph this, as c gets larger, so c starts at 0, then 1, then 2, then 3, then 4, then 5. Let me go from c is 0 to 10 here. And as I increase c, you see the value, the result, the function value, essentially the y value, gets closer and closer to some limit.
Yes.
So let me try having c go from 0 to 100. And let me scale down my chart here. Just want to scale the x down from 0 to 100. And actually just press the play button there. All right, there's my little train going, and you can see it goes pretty close to some limit, and then it doesn't really do much after that. So let's double check. Let's make this 0 to
Because it just flattens out.
100,000. Yeah. Is that enough zeros? 100,000?
Two
Yeah.
more.
And so it's getting closer to the 2.718 level.
1,000.
So.
There's
like,
10,000. There's, will it go? There's 100,000. All aboard. Doot doot. All right. And it doesn't do much after that. So if I scale back down and I look at the behavior, like what do you think my horizontal asymptote is?
The
Like what is it?
2.718, which is the
So if I say y equals e, and I'll make that a dotted line because it's an asymptote, just because that's what we're used to doing. And what's this? Now I'm 0 to 1,000. You can see that, press play, you can see that my little train starts off at,
Why does
So-
it speed up so much?
because the left to right motion is constant, but the up and down goes as fast as it has to keep up with the constant
Oh, I
motion
see.
on the x. So I'm telling the x variable, which is c here, to go at a constant rate as it goes left and right. And then no matter how far right we go, it just gets closer and closer to that number. So that number is the limit of that function. So that's what e is.
So
And you can see when I say y equals e here from my asymptote, it actually gives me the approximate value of e, 2.718-ish.
So E is just that function where x equals a really high number.
Where as x approaches infinity, f of x approaches e.
Alright.
Mr. Shadle, do you want that in our notes right there?
The function is
Well, the
the
example that you,
example of e.
yeah.
No, you don't have to do that.
I mean, it's not.
Max, you have a question?
What's the like significance of that function? Like,
What is it?
why does that function need its own like, its own number to show its asymptote?
I'll show you right now.
Wasn't it something to do with stocks?
So remind me what the what's the formula
It does compounding.
for discrete compoundings? First of all, what does discrete compoundings mean?
Where it just kinda goes up, like where you.
What is
add
discrete compoundings?
No, don't know.
The number of like individual compoundings,
So what does compounding mean?
like if you had 12,000 times 2 and then that number times 2 over and over again.
So if you invest $800 and this at 2% interest, then what happens after and its interest is compounded once per year? What happens for the first year that your money's in the bank?
Nothing.
It just stays $800. Your balance stays $800. What happens at the end of the year? What happens at the 1 year mark? Because it's interest is compounded once per year. What happens?
Turns into $816.
So you take 2%. What is 2% as a decimal?
0.02.
Right. So if I start off with an amount in the bank, then after the first year, I take my amount and times the interest rate, and I add it to it, and I get a new amount. Right?
Yeah.
Can I simplify this at all?
P times 1 plus R.
So I can factor out what terms do these terms have in common? What factor do they have in common?
P.
So I can take out a p, and that leaves me with 1 plus r. Right.
Mhm.
So at year 0, my balance was what?
800.
Yeah, it was just P. So my original P was just the amount that I invested. At year one, this is all year one, but it's a simplified way of doing it. I had P times 1 plus R. So whatever my original amount was, plus my interest rate, multiplied by my principal, gave me my new amount. What happens at the end of year two?
Wait, PR is interest rate, right?
It's the principal times the interest rate. But if I can simplify this, by taking out the P. That leaves 1 plus R as what happens at the end of that first year.
So are those, so PR is, that's times the interest rate, and then,
Yeah, so this would be $800 originally,
yeah.
plus $800 times, what is 2% as a decimal? 0.02, and that gives me my new amount. So they take 2% of your balance and they add it to your original balance. What happens at the end of year two?
Yeah.
It happens again.
It happened, yeah, when, yeah.
So I have my original amount. I had the amount from the previous year, and they do it again. So that's the new compounding interest. Compounding interest means it adds on to it. It builds up. So this is the compounding part. That's what compounding means. Can I write this in a simplified way? Can I write this more simply?
You could, wait, in that second parenthesis, is it 1 plus R?
It is.
Okay, then you could square it.
You're right. So I can write this a little bit more simply as squared. What happens at the end of year three?
Even to make it to the third power?
Right. I'm gonna write this out a little bit again. My previous one was this, and then it happens again. And then I can write this as what?
To the third power.
To the third? Okay, what happens after T years?
Wait, and I is interest, right? Or
There's no I.
or what is that?
This is number one.
Or one. Okay.
This is one because my original idea was I have the principal and then I add the principal times the rate, but these have a factor of P in common, so I'm rewriting it like this.
Why does it level out at even? Almost.
Well, we saw the graph. We saw our choo-choo train of
Yeah.
5 points
Yeah.
approaching E.
Yeah.
It's just the way of the universe works. It just does that. It just does that behavior. That's the way E was first discovered, but we've had many examples of how E is a very useful term. You know how else E is described? How else? How else, Jordan?
What?
It's the base of what? Oh, we'll get there. I'll tell you, base of the natural logarithm. So what is P sub t?
P R or 1 plus R to the 2.
1 plus r to the t, right? So this was to the first power. This is the second power. This is the third power. So we get, after t years, we get our original compounded t times. So that's the compounding interest. Discrete means it happens a certain number of times per year. Could be once per year, twice per year, 12 times per year. All right. So sometimes we might want to have quarterly compoundings, monthly compoundings, daily compoundings. So to make that happen, we're going to say let n equal the number of compoundings per year. And t is still the number of years. So we can upgrade this formula. Instead of P sub t, I'm just going to call this my account balance. that's P plus 1, or P times 1 plus the whatever the rate is divided by the number of compoundings per year, raised to the number of compoundings per year times the number of years. So this is equivalent to this when n equals 1. Do you see that? So I have r divided by 1 here. I have t times 1 here.
Oh, okay.
So it's the same formula. If n equals 1, we get this one. This was compounded once per year.
Okay.
So that's why those are equivalent. But if we want 2 compoundings per year, if we want to compound interest monthly, Emily, where are you in your computer? Close your laptop. CC, close your laptop. Take notes. Participate in class. Okay, so as we are trying to find how to do compoundings even faster. So this is our train here, going from
Wait, why are there
multiple what? Multiple cars on my train,
Yeah.
because I put in 5 points here.
Oh, okay.
Yeah, so this is C plus 1, C plus 2, C plus 3. So this is number of compoundings per year. Yeah.
I forgot, what is, like, I know the number of E, but what is E, like,
This is the limit.
2.7.
the limit?
This is the horizontal asymptote. This is the limit as I have more compoundings per year. So this is like, so this literally means that C plus 1 would be 1 compounding per year.
So,
C plus 2 would be twice per year,
so you can only have,
or 3 times per year, or 4 times per year, or 5 times per year.
so is that like the largest percent, or what, like, it's the limit of what?
This is the limit of how much so we started with the idea of compounding once per year. At the end of the year you compound interest, and then if that's n equals 1 and then n equals 2, that'd be twice per year. If n equals 12, that would be monthly, or if it's, let's say if n equals 4 times per year, that would be quarterly. N equals 12, that would be monthly. N equals 365, that would be 365 compoundings per year. And then as you get more and more frequent, this is what happens to your limit. It doesn't, it's like what if I compounded interest once per second? Or what if I compounded interest 10,000 times per second? Does the money in my bank account explode? No, it's approaching this limit.
Okay.
So some banks actually say, well, instead of compounding interest 10,000 times per second, let's just bump it up to the max. The max would be compounding continuously,
Okay.
and so then the train would jump up to the dotted line. Max.
I don't understand, because, like, if you're adding 2% once every...
2%?
No. Yeah, because if it's at 2% interest, right? Then if you add that once every, second, then it's gonna keep growing. It's not gonna have a limit.
It does keep growing, but it stops growing as fast, and eventually it stops at E.
Doesn't
Like
it
the-
keep
it's-
growing faster?
So you get
But
the
it's
2% of like.
So look at this. Watch this, Max. Up here, when n was 1, I was adding 2%. I was adding 2% each year. Now, on this one, if n equals 2, what?
Can I go to the bathroom?
Now I'm adding 1% twice per year. Or if I compound monthly, I'm adding 2% divided by 12.
Okay, so it's not
12
every
times per
time
year.
you add it.
Right.
You just
If it's compounded daily, I'm adding 2%, 2 divided by 365%, 365 times per year. So the formula kind of it's a little bit. You see the n in the denominator here. It's kind of slowing down the growth as it makes the compoundings happen more frequently. Lily, close your laptop.
I was trying to find, well, because your definition of E didn't make sense to me, so I was trying to find a better explanation.
Better than Mr. Shadle?
What?
Oh, Lily.
Oh my goodness! I am just all right. So we know that the limit of x as x approaches infinity of what was our formula from Desmos?
1 plus 1 over x parentheses to the x
Equals e, right?
equals, yeah.
So as x gets bigger and bigger, we get closer and closer to e. So let's try to reform our formula into e. Let's see what happens when we get more and more frequent. So if we start with this one, then allow me to let me introduce another variable here. I'm going to say let m equals the number of compoundings per divided by the rate. So I'm just gonna reform my formula based on this new variable. So what's my formula if I try to substitute in m?
P times 4 plus 1. So the
R over mr to the mrt. Okay, so I'm introducing a new variable and I'm substituting in for n. All so far so good?
Yeah.
Okay, can I simplify?
Yeah.
Simplify how?
P times 1 plus m.
What does this simplify to? Max, what does that simplify to?
I don't know.
1 over m.
1 over m.
How is that 1 over? Oh. Okay. I was looking at the next
Over
one.
m. And it's just in together.
Okay, I'm trying to get it to look like this.
Okay, it's getting there.
How can I get this to look more like this?
You put like the R and the T on the other side.
Okay, first of all, I'm going to take out the p because this doesn't have p in front, and then I have on the inside. This looks pretty good so far. And what do I want as my exponent?
Just
M. And what do I have left over? RT. Okay, and so
It's just P.
right. So the limit as m approaches infinity of this thing. So this allows me to have more and more compoundings. As I have 10,000 compoundings per second, 1 billion compoundings per second, 10 trillion compoundings per second. What is this? What's the limit of this? What's the limit of our little insert?
E.
E. What do I have left over?
RT.
RT. So we started with the formula for discrete compoundings, and this is our formula for discrete compoundings. Discrete meaning number of times per year. Discrete compoundings. And we've transformed it now into our Formula for what?
Continuous compounding.
Continuous compoundings.
So what's the formula for discrete compoundings again?
This one.
Okay.
Why is it different? Like, what's the difference between discrete and continuous?
Ah, wait a minute, I need that.
No way.
This is why it's different, because this thing, this function in the limit as x grows without bound it approaches this as x grows without bound, this thing f, it approaches e. That's why. So as m by itself goes to infinity, this becomes e, and then I still had p left over, and I had raised to the RT left over.
Wait, okay.
And then you want
The square brackets means it's not included, right? Just
Square brackets just allowed me to multiply this and raise it to this power with leaving the insides all alone, because that is the thing that approaches e, as we saw in our Desmos graph. So we have two formulas for compounding interest. We have one for discrete compoundings. If they say interest is compounded daily, which one do you use?
Discrete compounding.
The first one, and n is what?
oh, that's the formula for
1 over
okay.
365.
N is what?
360.
365.
So the
And this formula is for, they say interest is compounded continuously, you use PERT.
does the
Okay,
does
and
the
that's-
p times 1 plus
So
1 over mrt to the mrt, is that also part of the continuous compounding, or is that part
No,
of
this is the derivation. This is how we got from from discrete to continuous, because whatever m is, m was just r over n over r. We let m approach infinity, and that caused this interior part to convert to e. So this is allowing our graph to grow without bounds. So you're getting closer and closer and closer, and we just said, well, what happens in the limit as x approaches infinity?
you don't have to
Yeah.
Did that help at all, Max?
Yeah, I
Ish,
think so.
sort of. So the things you need to know are the ones that I've highlighted. These are the ones that you need to have on your index card for quizzes and tests, and when to use them. But you don't need to know all this intermediate stuff. The intermediate stuff was just to show you how we got from the one formula to the other.
Can I take a picture of this just because I want to go? I just want to spend some time
You can.
going over it.
Yep.
Okay, thank you.